Hello, I'm Anindya Mondal, an undergraduate student in the Department of Electronics and Telecommunication Engineering in Jadavpur University, India. Today I'm going to present my work on moving object detection for event-based vision using graph spectral clustering. This work has been done as a part of the collaboration between my department and the Mathematics, Image and Applications Laboratory of La Rochelle University, France. Our work is organized as follows. Before going into the detail of our work, let us discuss what are event-based cameras. So event-based cameras are bio-inspired cameras that mimic the working of a human eye. These cameras captures only the motion in a scene, opposite to frame-based cameras which capture both the moving and static objects. This is because these cameras sample light based on the scene dynamics rather than a clock which exists in case of frame-based cameras that has no relation with that of the viewed scene. For these reasons, event cameras have multiple advantages over frame-based cameras, like low latency, reduced motion blur during high motion, low power consumption, and high dynamic range. In spite of the advantages, there are a few challenges that needs to be dealt with. The reasons are that pixels in event-based cameras generate asynchronously with scene dynamics, and the event data lack visual features like that of texture and color. So processing event data requires special algorithms to be designed, and traditional algorithms that are used to process frame-based data is not always applicable for them. For detecting moving objects in event-based data, there has been some previous approaches based on parametric models and traditional clustering algorithms. However, parametric models require the optimization of multiple parameters, and success of the model depends on the careful choice of the parameter values. Whereas traditional clustering algorithms like Gaussian mixture model, TB-scan, and min-shift require extensive pre-processing of the event data and are also sensitive to noise. We must keep in mind that event-based sensors are very much noise sensitive. This is because of the technology is very novel and we need to take care of the generated noise. So to tackle these challenges that has been mentioned before, we propose a GSC event mod or the Graph Spectral Clustering for detecting moving objects in event-based data. Our method improves upon the previous methods in a multiple ways. First is that the performance improvement over the state-of-the-art method is high as much as 30%. We use graphs as we know that graphs can better deal with irregular data, and event-based data is irregular and of arbitrary shapes. Also, we use a silhouette analysis, which is a state-of-the-art method for determining the optimal number of clusters. So the methodology, to summarize our methodology or proposed method, it consists of three parts. First is the sampling of the event data and graph construction. Following that, performing graph spectral clustering on that graph, and finally obtaining the optimal number of clusters. So this is the diagram of the framework, and which we will be discussing later. First is the sampling and graph construction. So what we do is that we represent the events as points in a 3D spacetime graph. And the spacetime graph is divided by the number of image frames to get meaningful samples. That is in our in the camera, in dataset, we have their corresponding frame-based images corresponding to that of the events. And we divide the whole 3D sequence into those partitions, depending upon at which timestamp those frame-based images are being captured. Each of these partitions now contains certain number of events which are being taken for constructing a k nearest neighborhood graph. The value of k has been taken such that we can have a trade-off in between the high noise sensitivity when the value of k is low and high computational complexity where the value of k is high. The value of k, that is the nearest neighbors, is being determined experimentally. Now we obtain the graph Laplacian from the constructed graph. We obtain the unnormalized graph Laplacian by finding the difference in between the degree matrix and the adjacency matrix. Following that, we perform eigen decomposition on that Laplacian and obtain the eigenvalues and eigenvectors. Those eigenvalues are then arranged in ascending order of their magnitude. Now, out of that n eigenvectors, as we have mentioned here, we build another matrix U by taking the first k eigenvectors. By first k, we mean in ascending order. The value of k will be determined later, which we will see in the next slides. This matrix U contains the eigenvectors ui to uk as columns. Now we consider the row vectors of U and perform k-means clustering on the row vectors of that matrix U. By this, we obtain the clusters C1 to Ck, determine if we consider their k clusters. Thus, each of those row vectors or points are being assigned to their corresponding cluster labels. For example, if there are three clusters, C1, C2, and C3, each of those row vectors or points will be assigned to which clusters they belong, whether on C1, whether on C2, or whether on C3. Now, determining the optimal number of clusters, as we have mentioned before, we use silhouette analysis, which is a state-of-the-art method for detecting the optimal number of clusters. Silhouette analysis measures the difference in between the within cluster tightness and separation from the rest. In our work, we take different values of k and calculate the silhouette value for each k. And the value of k for which it returns the maximum optimal value is being considered as the optimal number of clusters, which in case in our work is the number of moving objects in a scene. This way we find out the value of k as mentioned here and also as mentioned here.
Hello everyone, I'm Shashant from the Department of Electronics and Telecommunication Engineering, Jadavpur University. Let's move on forward to the experimental section of our paper. We took the help of DVS Motion 20 dataset that was developed by Al-Matrafi for their work on distance surface for event-based optical flow. And the dataset includes two sequences, namely the car sequence and the hand sequence. The hand sequence is an indoor scene, and the outdoor sequence is the car sequence. We also took the help of a synthetically generated dataset, and we call that the street sequence. It was developed using the video to events framework, which was developed by Hu et al. In 2021. Let's move on forward. And here, these are the visual results of our GSC event mod algorithm. And here you can visually see and understand the efficiency of our model in all the three sequences. Here, we also did a comparative study, both qualitatively as well as quantitatively. And from this slide, you can see the performance of each of the algorithms and in all the three sequences. And it is clearly evident that our algorithm, GSC event mod, outperforms the rest. This is the performance of all the well-known clustering algorithms in the synthetically developed sequence, the street sequence. Okay, so quantitatively, what we did was for quantitatively verifying our results, we accumulated the events corresponding to their grayscale frames in different time intervals. As a desktop dataset does not have labeled data, they do not have the ground truth. So we labeled them manually. You can have a look at this table and get an idea of the performance of different clustering algorithms in the three sequences. And it is quite clearly evident that GSC event mode outperforms the previous well-known clustering algorithms in this dataset. In conclusion, I would like to summarize by reiterating the following points. Our work introduces the use of graph spectral clustering for detecting moving objects in event data. Our method shows performance improvement over state-of-the-art methods. We use silhouette analysis to detect the actual number of moving objects in a scene. And in the future, we plan to extend our work to use semi-supervised learning methods for improving detection accuracy, and incorporate motion models for extending the framework to tracking. Thank you. These are my co-authors, and feel free to contact any of us in case you have any queries. Thanks a lot.